Okay, good morning guys. So today I want to talk about optimizations for calculus. So here's one of the classic problem for optimizations. So you have 40 feet of fence to enclose a rectangular garden. So what's the maximum area that you can enclose? So first thing that you want to draw is the figure. So it's a rectangle. So we do have the width, which is x. And then the length by using the perimeter, so which is 40 minus 2x divided by 2. Because the perimeter of a rectangle is 2 width plus 2 length, so that equals the perimeter. And then you just isolate the variable L, so we got 20 minus x. And then the area of a rectangle is always length times width, so we got x times 20 minus x. Because you're not allowed to have two variables for the optimization problem. So we just eliminate one variable, so we got one variable right now. And consider that ax to be the area formula as a function of x. So what's the domain? Well, obviously that the domain cannot be more than 20. So that means x must be less than 20, but it must be greater than 0 because that's about the dimension, the distance, or the length. And the way that we can find out the area, so simply just multiply it out, so it turns out to be a quadratic equation. And then take the derivative, so we got 20, and then minus, using the power rule, 2x. And we set it equal to 0, so we can solve for x. So x, which is 10 feet, and x, again, that's just a reminder, which is just the width. And to find the length, so just plug in the number back to the substitutions equation, so we got 20 minus 10, which is 10 feet. Again, this one is just like one of the traditional optimization problem. So as you can see that we do know that square can be a rectangle, but rectangle cannot be a square. And the way to solve for the problem involving optimization, so here's some of the steps and process that you need to follow through. So first one, always draw the picture, and this problem really requires that you get a good look at what you're trying to find. So it's always going back to geometry. So for geometry there's so many like those type of structural problem. Rectangle shapes, figure, two-dimensional, three-dimensional, volume, so you'll talk about like three-dimensional figures such as prisms, triangular prisms, cones, cylinder, things like that. And then after that you want to label the dimension in terms of one variable, so you don't want to use two variable. Again, calculus, AB, it's all about single variable. And then step 3, you want to find a function that in terms of x to represents what maximum, minimum value you're trying to find, and be sure to define the domain for x. And then take the derivative, set it equal to zeros, and find the critical points. Because once we find a critical point, we can always do the first derivative test, so we can find out whether that's a max or min. And then check the critical point, and don't forget the endpoint. So here's another problem. So you have 40 feet of fence to enclose a rectangular garden along the sides of a barn. And what is the maximum area that you can enclose? So we do know that one side is solid, so there's no fencing here, so it's only for the two width and the other length. So once again, W equals x. And then for the length, so we do have 40 minus 2x. Again, this side right here, it's not included, so that's why it's 40 minus 2x. Again, the area of a rectangle is always length times width, or width times the length. So we put in all the variable, x times the quantity of 40 minus 2x. And then distribute, so we got 40x minus 2x squared. And now from here, since we do have a standard form, we can just take the derivative term by term. It's easier. I mean, you can take the derivative from here as well, but that means you have to use the product rule, which is a little bit more complicated. Again, once we find the derivative, we set it equal to 0, so we can solve for x. So that means x is 10. And then the unit for that is 10 feet, which is the width. And there must be a local maximum here, since the endpoints are minimum. So we find the length, and then we find the width. So the way to find the area, so we just plug in that, the width, the length, all the way back here. So we got 10 times 20, which is 200 square feet. And now here's another problem, that you're making an open top rectangular box, and from the dimensions of a cardboard, which is 8 by 15 inches for the dimension, and anytime that you want to make the open top box, you always want to cut off the corner. So let's say that each corner it's x for the dimension, it's a little square. So you want to find the dimension of such a box with the largest volume. So here's another classic problem. So each square that we cut off would have a size equal to x. Okay, so that's what we got here with the label. And do we have a limit domain for x value? Yes, we do. It's from 0 to 4. But why? So that's one thing that you guys probably want to think about. So here's the reason. So suppose that x measures larger than 4 as shown to the right. And it wouldn't make sense for 2 squared to add up to 8 or more inches. And again, the way to find out the volume of a rectangular prism, it's length times width times height. I'm sure here's the formula a lot of people are pretty familiar with. Back to geometry. So length, width, and height, three-dimensional, so it's a three-dimensional figure. Now all we have to do is just find out that dimension in terms of x. So for the dimension of the box here, the length, it's just 15 minus 2x, because we cut off the corner. And then for the width, quite similar, so it's 8 minus 2x. And the height, guess what that is? That's right, it's just the depth, which is x. And here's the formula for the volume in terms of x. And before you do that, you want to multiply, FOIL, distribute. So eventually, you're going to end up with 120x minus 46x squared plus 4x to the power of 3. To maximize the volume, so we can find a critical point and then use them to find the maximum. So from there, you want to take the derivative. So we got 120 minus, using the power rule, 92x. And then plus 4 times 3, 12, x squared. Again, it's all the power rule. And now you want to set that equal to 0. And back to algebra 2 and pre-calc, we want to factor this a little bit. So once you factor it, and then solve for x, we do have 5 over 3 and comma 6. But we do know that 6 is not the domain for x for both endpoints. So the only solution we have right here, which is just 5/3. So be sure that 5/3 is in the x-coordinate of the maximum value for v of x. So now here's the dimensions for the length. So 15 minus 2 times 5/3, we just plug in the number back to the original setup. So it's 35 over 3 inches. And then the width, a minus 2x, so a minus 2 times 5/3, 14 over 3 inches. And then the depth is just 5/3. And by plugging all the numbers back here for the volume, so we got 90.774 inches, cubic inches. And here's another example. So what dimensions for 1 liter cylindrical can will use the least amounts of material? So if that's using the least amounts of material, so probably want to think about that. Is that the volume, the surface area? Indeed, it's the surface area of the cylindrical can, at least. So that means we want to minimize the material of the surface area. So the surface area for the cylinder, it's considered 2 pi r squared, because we do have the upper base, bottom base, which they're all circles, circular bases. So 2 pi r squared. And then 2 pi r times h, which is the lateral area of the cylinder. Again, we do have too many variables here. We do have radius, we do have the height, So here's one thing we need to find out. So we need another equation that related R and H. So one thing that we notice is that volume of the cylinder, it's always pi r squared times the height, which is the base times the height, the area of the base times the height. So 1 liter equals 1,000 cubic centimeters. So let's say that we do have a volume for the can, which is 1,000, 1 liter. That's just like a normal standard scales for any kind of like a motor oil can. And so that's what we got, 1,000 equals pi r squared h. And now from there, we want to solve for the height. We want to solve for the height in terms of radius. So divide it, 1,000 divided by pi r squared. And now back to the main equations. We want to convert that in terms of r. So 2 pi r squared, we don't change anything there. But now for 2 pi r times h. So instead of using h, we're using 1,000 over pi r squared. So this one is kind of like going back to linear system equation. So it's like a direct substitution. And then we cross cancel the pi, the r. So we left with 2,000 over r. Again, 2 pi r squared, we don't change anything for that. And take the derivative. So we got 2 pi r squared using the power rule. So we got 4 pi r. And then using the quotient rule, or you can convert that to like a product. We can use the product rule, which is negative 2,000 over r squared. And now we want to set the equation equal to 0, the first derivative. And then we solve for r. So we can use that as a proportionality form. So 2,000 over r squared equals 4 pi r. And then cross multiply, we got 2,000 equals 4 pi r to the power of 3, or 4 pi r cubed. And then solve for r. So we need to isolate the constant, divided by pi, and then we take the cube root of the whole quantity. And the radius is about 5.42 centimeter. And then plugging the number back to the original equations, the auxiliary equation for the volume. So we got 1,000 divided by pi times 5.42 quantity squared, then that's the height. So the height, it's about 10.83 centimeters. And notice that, and reminder, so if the function that you want to optimize has more than one variable, so make sure that you have to use the substitution to rewrite the function in terms of just one variable, because you're not allowed to have more than one variable to differentiate the equation. Again, this one is considered singular variable calculus, so that means we try to limit to one variable. So once you get into like calculus 2 or maybe multivariable calculus, you'll deal with more than one variable with the equation. And then if you're not sure that the extreme you found is maximum or minimum, you can always check that. Or you can use that the first derivative line test. And if the endpoint could be the maximum or the minimum, then you have to check. And thank you for watching the video today.